Namaskar. Today we'll discuss queuing theory. Queuing theory is also called as waiting line theory. In this lecture, we'll discuss what is queuing theory or what is waiting line theory, why it is important tool. We'll see some examples. Then components of queuing systems. Then exponential distribution and queuing system we'll discuss. Then we'll discuss the process, then some terminologies, notations, Little's formula, birth and death process we'll discuss. So what is important? So important queuing model is FIFO, that is first in first out discipline. So there are different types of models we'll discuss. Then priority discipline queuing models, application of queuing theory to the system design and decision making. So all these points we'll discuss in today's lecture. So let us discuss first what is queuing theory. So why it is required? So queuing theory or waiting line theory, it owes its development to A.K. Erlang. So he in 1903 took up the problem on congestion of telephone traffic. So the difficulty was that during busy periods, telephone operators were unable to handle the calls the moment they were made, so resulting in delayed calls. So that's why he developed this theory. So businesses of all types, industries, schools, hospitals, cafeterias, bookstores, libraries, banks, post offices, petrol pumps, theaters, all have queuing problems. So further examples of queues through less apparent are waiting for a telephone operator to answer, the traffic light to change, the morning mail to be delivered, and many. So waiting line problem arises either because time is too much demand on the facilities, so that we say that there is an excess of waiting time or inadequate number of service facilities. So there is too less demand. Sometimes there is too less demand, in which case there is too much ideal facility time or too many facilities are there and these facilities are waiting for customers. So in either case, the problem is to either schedule arrivals or provide proper number of facilities, or both, so as to obtain an optimum balance between costs associated with waiting time and ideal time. So operation research can quite effectively analyze such queuing or congestion phenomena. So in operation research, so there are many cases of waiting line theory. Okay, so almost all business situation it is required. Waiting line theory is also widely used in manufacturing units. It has been popularly used in the area of tool cribs. So there is a general complaint from the foreman that their workmen wait too long in line for tools and parts. So though the management wants to reduce the overhead charges, engaging more attendants can actually reduce overall manufacturing cost, since the workers will be working instead of standing in line. So waiting line theory is so another problem that is solved in construction. Okay, number of docks to be constructed for trucks and ships. So it is also applied in the problem of machine breakdown and repairs. There is also waiting is there. So queuing theory has been applied for the solution of problems such as scheduling of mechanical transport fleets, scheduling distribution of scarce war material, scheduling of jobs in production control, minimization of congestion due to traffic delay at tool booths, the solution of inventory control problems, So in many cases, in all of these cases, the queuing theory is applied. So mathematical analysis of queues and waiting time in stochastic system. So used extensively analyzed production and service processes exhibiting random variability in market demand and service times. So queues arise when the short-term demand for service exceeds the capacity. So most often caused by random variations in service time and the time between customer arrivals. If long-term demand for service, the capacity, the queue will explode. So waiting line or queues are familiar phenomena which we observe quite frequently in our daily life. The basic characteristics of queuing phenomena are unit arrival at regular or irregular interval of time at a given point called the service center. So one or more service channels or service stations or service facilities, for example ticket windows, typist, docks, etc., are assembled at the service center. If the service station is empty, the arrival customers will be served immediately. If service station is not empty, the arriving customers will wait in line until the service is provided. Once service has been completed, the customer leaves the system. Whenever we have customers coming to a service facility in such a way that either customers or facilities have to wait, we have a queuing problem. So capacity problems are very common in industry and one of the main drives of process redesign. So here need to balance the cost of increased capacity against the gains of increased productivity and service. So this is very important in such case. If customers are more and your facility is less, you can increase your capacity, but to increase this capacity the cost is required and this should be balanced with your earning, your increased production. So queuing and waiting time analysis is particularly important in service system. So large cost of waiting and of lost sales due to waiting is considered while designing a new system or increasing capacity. So if you take an example of county hospital, any hospital, then you come to know that the patients arrive by ambulance or by their own. So one doctor is always on duty and more patients seeks help, longer waiting time. So this is one example. So here there is a cost and capacity. So cost reduces as waiting. So cost of waiting reduces when you increase capacity, but when you increase the capacity, so there is a cost of service increases. So you have to consider one point, optimum point. See here, dotted black line shows you the cost of waiting. Initially, if service facility is limited, the cost of waiting is high. When service facility increases, then cost of waiting reduces. But at the same time, when service facilities are added, the cost of service increases. So these two curves are crossing at one point. So this blue line, blue curve, the cost of increases as capacity increases. Then you have to consider that intersection point where the cost of service and cost of waiting are meeting each other. So we have to consider this. So let us see the examples of real world queuing systems. The commercial queuing systems. So commercial organizations serving external customers For example, dentist, banks, ATM, gas station, plumbers, garage, etc. So one service provider and number of customers are there. In transportation service systems, vehicles are customers or servers. Vehicles waiting at toll station and traffic lights, trucks or ships waiting to be loaded, taxi cabs, fire engines, elevators, buses. So these are some examples. Transportation system where waiting is applied. Then some business internal services, customer receiving services are internal to be services are internal to the organization providing the service. The inspection station, conveyor belts, computer supports. Some material arriving to that business center, so it should be get checked first and then it's entered. So that is a queue is there. The social service systems, that is judicial process, the hospitals, emergency relief hospitals, then waiting list of organ transplant or student door rooms. So these are some service sector where this queuing system is applied. So here if you divide the components of queuing systems, okay, input system, so input system are different, okay, so calling populations, so arrive, then queue is there and then service merchant is there. Okay, queuing system consists of queue and service center. So on the screen you can see the serve job is there, the leave, the system leave is there, but here what are the important things? So calling populations means number of people arriving or input, then arrival process, which type of arrival, then queue configuration, then queue disciplines and service processes. So these are some important components of queuing process. So let's discuss one by one. So calling population, that is customer. So the customer, the arriving unit that requires some service to be performed. As customer may be person, machine, vehicles, parts, etc. So the population from which customer or job originate is called calling population. Size can be finite or infinite. So the calling population can be homogeneous, only one type of customers or jobs, or heterogeneous, or several kinds of customers or jobs. There are different types. Okay. Then second is arrival process, how it arrives. So this is also one important basic component. Okay. So determines how, when and where customer or jobs arrive to the system. Important characteristics is a customers or jobs enter arrival times. To correct specify the arrival process requires data collection of interval times and statistical analysis. So this is about arrival process component in basic queuing system. In queue configuration, how queue is configured. So number of customers waiting to be served. The queue does not include the customer being served. So here queue configuration, the specific number of queues, single or multiple line to the number of service stations, their locations, their effect on customer behavior, backing and reneging, the maximum size of the queue can hold. So distinction between infinite and finite capacity. See, there are two queue configurations. One is multiple queues and single queues. So you can see in the first figure there are number of black holes. Okay, the number of rows are there. Okay, lines are there. So 4 service center and 4 rows are there. Okay, so it is a multiple queues at the same time. All 4 queues lines customer can go. And here single queue system is there but 4 stations are there. Whichever empty, just go and start your this. So in this way, there are 2 types of queue configuration systems. So in multiple line advantage, the service provided can be differentiated. A supermarket express lanes. So labor specialization possible. Customer has more flexibility. So backing behavior may be deterred. So several medium length lines are less intimidating than one very long line. What is the single line advantage? So single lines are guarantee fairness. So first in, first out applied to all arrivals. No customer anxiety regarding choice of queue. Avoid cutting in problems. The most efficient setup for minimizing time in the queue. So joking, the line switching is avoided. So these are some advantage of single line. See here, single line queue and multi-line queue, multiple line queue. The service mechanism is also important. So what are important components we are discussing? See here, it is a calling population, then arrival process, queuing configuration, queuing discipline and service processes. So we are discussing one by one. Here, service mechanism. Service mechanism, the process or facility which is performing the service to the customer. So this may be single or multiple channel. The number of service channels is denoted by the symbol C. Let service mechanism can involve one or several service facilities with one or several parallel service channels. Specification is required. The service provided by server is characterized by its service time. Specification is required and typically involves data gathering and statistical analysis. Most analytical queuing models are based on the assumptions of exponentially distributed service times with some generalizations. So the queue discipline is also important. This specifies the order by which job in the queue are being served. So most common used principle is FIFO, that is first in, first out. Then other rules are there. For example, LIFO, SPT, RED we will discuss later. So can entail prioritization based on customer type. Depends upon type of customers. So you can give priority. Then mitigating effects of long queue. So what are effects of long queue? So cancelling the queue from arriving customers. So restaurants divert people to the bar or use pages. So amusement park require people to buy ticket outside the park. Bank broadcast news on TV at various stations along the queue, casinos, nightclub queues. So through slot machine areas, so you can use this. Then use the customer as a resources. The patient filling out medical history form while waiting for physician. So making the customers wait comfortable and distracting their attention. Complimentary drinks at restaurant, computer games, internet stations, food courts, shops, etc. at airport. Then explain reason for the wait. Provide pessimistic estimates of remaining wait time, that wait seems shorter if a time estimate is given. Fair and open about the queue disciplines used. So these are some effects of long queues. So commonly seen queuing model. So this is one of the model. So there are customers arriving and the queue system is there and number of service facilities. Here the arriving unit that requires some service to be performed, that is a customer. As already described, the customer may be person, machine, vehicles, parts, etc. Then queue, waiting line, that is a in queue customer is there, number of customers waiting to be served. So queue does not include the customer being served. Then service facilities. So these are commonly seen queuing models. This is one model. So service time as well as interval time are assumed independent and identically distributed if not otherwise specified. So commonly used notations are A, B, C. A is the inter-arrival time distribution. B is the service time distribution. C is the number of parallel servers. Then commonly used distributors and distributions. M, that is Markovan exponential memory. Then D stands for deterministic distribution models. Then G stands for general distribution models. So for example, MMC, that is queuing system with exponentially distributed service and inter-arrival times, and C services. Okay, so these are some common problems. So the exponential distribution and queuing, the most commonly used queuing models are based on the assumptions exponentially distributed service times and inter-arrivals. So the stochastic or random variable T exponential I, that is the exponential distributed with parameter alpha, if its frequency function is given, you can see. So this is about exponential distribution. There is probability density and service time. So it represents the pattern in which the number of customers have the service facility. So departure may also represents by the service time, which is the time period between two successive services. Service time may be constant or variable but known or random. So if services times are randomly distributed, we have to find out what probability distribution best describes their behavior. In many cases where service times are random, management scientists have found that they are best described by exponential probability distribution. If service times are exponentially distributed and arrives Poisson's distribution, the mathematics necessary to study waiting line behavior is somewhat easier to develop and use. Here this figure illustrates an exponential probability distribution of service items on service times. From this, we find that the probability of long services time is rather than small. So rate at which one service channel can perform the service, that is number of customers served per unit of time, is called serving rate. So this rate assumes the service channel to be always problems. Many causes of uniform service rate will be found there of uniform arrival rates. So this is about exponential. So exponential distribution. So relationship to the Poisson's distribution and Poisson's process is shown. Then stochastic process in continuous time. The stochastic process in continuous time is a family. A function of time. The stochastic variable defines over a continuous set of T values, the number of phone calls connected through a switchboard. So stochastic process is said to have independent increments if for all disjoint intervals the differences are mutually independent. The Poisson's process, the standard assumption in many queuing model is that the arrival process is Poisson. So two equivalent definitions of Poisson process are the time between arrivals are independent, identically distributed and exponential. Then X is the Poisson's process with arrival rate. The state of the system equal to number of customers in the system. So queuing length is the state of the system minus number of customers being served. So we must know these terminologies and notations. That is number of customers, the probability that time, average arrival intensity, average service intensity. These are some examples. So in service utilization factor, we can use this system. In queuing theory is focused on steady state conditions. So enough time has passed for the system state to be independent of the initial state as well as the elapsed time. The probability distribution of the state of the system remains the same over time. What are transit conditions? So prevalent when a queuing system has recently begun operations, the state of the system is greatly affected by the initial state and by the time lapse since operation started. The probability distribution of state of the system changes with time. So illustration of transient and steady state conditions. So you can see here the NT, the number of customers in the system at a time T, represents the expected number of customers in the system. So notation for steady state analysis here are Pn, the probability that there are exactly n customers or job in the system in steady state. Capital L, expected number of customers in the system. LQ, expected number of customers in the queue in steady state. Capital W is expected time a job spends in the system. And WQ is expected time a job spends in a queue system. So you note these notations. So these are used in steady state analysis. In next session lecture we'll discuss these things in detail. We'll see some few examples also. So one more time, there is birth and death process. The foundation of many of the most commonly used queuing model is birth and death. See, so equivalent to the arrival of the customer, birth is equivalent to arrival of the customer or job. This arrival of one person on the earth, and death equivalent to departure of served customer or job. So what are assumptions in such case? Here are some assumptions. So give for nt is small n, the time until the next birth. TB is exponentially distributed with parameter lambda n. The customers arriving according to the PO process. The remaining service time TD is exponentially distributed with parameter mu n. TB and TD are mutually independent stochastic variables and state transition occurs through exactly one time birth. So see here the excellent tool for describing the mechanisms of birth and death process. Here lambda is used. This is a parameter for customer arriving, and mu n is okay. So here So excellent tool. It is, you can see in on a screen. Here it is state n, that is the case of number of customer jobs in the system n. So number of arrival, number of departure. So lambda minus u, lambda minus u, mu. Okay. So there are some assumptions of MM1 models. So we'll discuss this part in next session of this lecture. Okay. So if you have any doubt, you can write in your comment box. We'll discuss this same topic. We continue same topic in next lecture or next session. Also put your roll number and name in a comment box. I will consider that as a attendance. So you try to like this video. You can share this video with your friends. And if any doubt is there, you can ask. I will answer in next video. Also I will engage one doubt clarification session where you can join in next lecture. Okay, thank you very much.